Fingerprints are by far the fastest way to authenticate on modern devices, and they're so good we've been literally using them for centuries.
But how does it work?
To find out, I decided to build fingerprint recognition from scratch for a university project. Now that decision was either very ambitious or a terrible overestimation of my own skill, because it still doesn't work, and the deadline is in 5 days. If I can't pull this off, I will be in trouble, academically speaking. This has to work.
Will I triumph over the technology, or will I be punished for my hubris? We'll see. So let me get you up to speed.
The plan is as follows. 1. Take a fingerprint image. 2. Reduce it to clean, thin, ridged lines. 3. Find key points, ridge endings, and splits called bifurcations. Compare those points to a stored template to get a similarity score. The fingerprints are considered similar if they have the same features in the same places. All of this would be fairly straightforward to do in software. But we aren't doing things the convenient way, of course. This is an FPGA. Basically, a blank slate of processor silicon that you wire into existence. And this is the cheapest optical sensor I could find on AliExpress. What could ever go wrong? We are doing all of this by creating specialized hardware. Instead of defining functions and variables, we define signals that interact with components. Instead of lines of code executing in series, we build hardware modules. So each function is basically its own microchip. Writing code for a normal CPU is like giving a hyperactive chef a to-do list. They can only execute one instruction at a time, but they read that list incredibly fast. If you make a mistake in one of the steps, the chef just stops, throws an error, insults you, and points to the exact line where you messed up.
The f***ing bus is f***ing wrong!
An FPGA doesn't do that. It doesn't read lists, there are no guardrails or error handling. Writing a hardware description language is like building a massive, intricate marble run from scratch. And instead of processing one thing at a time, thousands of marbles, bits, are dropping through the machine simultaneously. This approach is, of course, extremely powerful because it allows us to do endless optimizations. But if you make a track 1mm too short or a trapdoor opens a fraction of a clock cycle too late, the marbles don't just stop and give you an error code. They overflow, they jam the gears, they cascade into catastrophic, invisible failures that might ripple through the entire thing, meaning that one small, seemingly isolated mistake can create ripple effects throughout the entire design, which surely will not be relevant later. Let's start from the progress I have already done on this project. Before we can even think of doing anything with an image, I need a way to talk to the board, so I cooked up a simple UART interface. It's just 2 wires and a protocol to use them. 1 start bit, 8 data bits, 1 redundancy check, 1 stop bit. Nice.
Have an orange light. Good. But LED number 15 should light up. So why is it not lighting up?
Now, to get to thin profile lines, first we need to convert every grayscale pixel into either black or white. So behold, the binarizer subsystem. The window reader slides over the image in a 3x3 pixel area and outputs the grayscale values. The threshold builder also reads the image, but it outputs an average of the grayscale values in an 8x8 area, which we use as a local threshold. Computing local thresholds is necessary because otherwise entire chunks of the image would be turned monochrome by the comparison logic. Apparently brightness is a thing. Who would have thought? That was hard, but overall I was feeling hopeful, and I had made the window reader, which is the keystone of my image processing. I had no idea though about the Dark Souls level boss fight I was about to face. And now we get to the stuff that isn't done, which is where our 5 days start. I want to preface this by saying that this video should be an example of why you absolutely shouldn't try to complete projects on an insane time crunch like this. Please learn from my mistakes. The thinning subsystem implements an algorithm that takes binary blobs of the image and puts them on a diet to make them into healthier, clean lines. To do that, we need to use the aforementioned window reader to scan the image and for each snapshot take a single decision. Leave the center pixel as is or remove it from existence. Do this several times until only a skeleton is left. This is what we call an iterative process, meaning that we repeat until a condition is reached. In hardware, that's tricky because each iteration reads the output of the previous one. And since the loop only stops when it sees that no more pixels are deleted, meaning clean lines, because we don't know how many iterations it will take, I could not just chain a fixed number of buffers. The solution are ping-pong RAMs. It's a technical term, I swear. Each iteration reads from one and writes to the other. The part that gave me the biggest headache was actually the pixel deletion logic though. In this case, a simplified version of the Guo-Hall algorithm. And eventually I did manage to get it working by the end of day 2. At day 3, now that we have a 1 pixel wide skeleton of the fingerprint, we extract the features that make the fingerprint unique. That is ridge endings, which is where the line just stops, and bifurcations, where it splits into 2. All of those points are stored in a template. We call these features minutiae, and hence the minutiae extractor. For each center pixel that's part of the ridge, it looks at the neighbors and it runs a tiny classification test. It computes two small numbers, n and cn. N is how many neighboring pixels are set, meaning they are 1, which in this case is represented as black, and cn, how many times you see a white to black transition when you walk around the neighbors in a loop. In my case, I chose clockwise. And the rule is actually beautifully clean. Cn equal to 1 means we have a ridge ending, Cn equal to 3 means we have a bifurcation, anything else we ignore.
We should, yes. First stage is going, and we have an output. I mean, it is ugly, but it is an output.
So that too finally was working. And it was the night between day 3 and day 4, and little did I know what was left would be somewhat easier but infinitely more stressful. Up to this point, everything was in hardware. We had UART, we had binarization, we had thinning, and we had minutiae extraction. Originally, I wanted to do the matching logic in hardware too, but as you can imagine, my stress was through the roof since I was running out of time. So I decided to create what we call a soft-core CPU. That just means that instead of an actual processor, it's something implemented inside the FPGA logic. So I did that in order to be able to run some C code on it. And by that, I mean take a pre-made CPU in VHDL and chuck it in.
Okay, so if the CPU is working correctly, I should be able to press reset on the board and there should be something. Yes. Now we press U. Then yes. Okay. And I input the file. Please don't blow up. Okay, it didn't blow up. Holy sh. Holy sh. Okay. Okay, now E to execute. It is booting. It is done. I mean, it's not done, but it's something.
Which of course was harder than expected, but at this point that's kind of a constant.
Nothing. Yeah, nothing. So we should have... Yes. Yes. We finally have a green light. Good.
The CPU was finally operational at the start of the last day. All the stages were completed, so I was basically done, right?
Wrong. Second stage. Yes. Third stage. Also yes. And what? Why 18?
I thought that it was working, but well, it wasn't. The similarity scores produced by the board were very inconsistent. They basically looked like random numbers being generated. Additionally, you might have noticed this nice screen output. I had made that too through a VGA interface to basically try to look at what was happening inside the board.
Also, there are alternate modes. We have a fingerprint and a fingerprint.
And only now I was starting to doubt its accuracy. Remember when I told you that hardware is unforgiving? Debugging all of this meant fighting this spaghetti monster with my bare hands. So I was less than 24 hours from the due date with a project that just wasn't ready. And I was genuinely starting to think I would make it. All of the work done so far, all of the stress, just to not be able to turn in the project in time.
Okay, we'll try again. We have communication. Green light, green light, green light, green light. Okay, now let me try to... It should be all ones. I should see 1 1 1 1. What the fuck is that? Why? Why?
Not because the idea was bad or because the logic was flawed, but because I had run out of time to make the last 10% of it behave. But as I told you at the start, this had to work. There was no backup plan. So I looked at the spaghetti monster straight in the eyes, and I remembered one very important thing. I am Italian. So I sat at my desk, I kid you not, for 9 straight hours. And eventually, at around 168 microseconds into the simulation for when the data was being into one of the RAMs, I found the murderer. It was not a logic error, the math was correct, the logic was fine. It was a timing error. To understand what went wrong, you have to remember that an FPGA acts like a very elaborate marble machine. In the minutiae extractor stage, the marbles move to calculate the features of the fingerprint, the XY coordinates, and the distinction between ending and bifurcation. Then, they're in a box with a valid sticker on it, and sent down the conveyor belt to be saved into memory, which is called the BRAM. The BRAM opens the box, reads the value, and notes it down in its own module. In my code, I was telling the memory module to save the data on the exact same clock cycle that the data was being packed. So I was effectively trying to grab the box at the exact same millisecond that the items were being put inside. Because the data wasn't stable yet, the memory was seeing ghosts, basically. It sampled a partially updated value, meaning the very first feature recorded in memory had its valid bit set to 0, which means false. Because the first record was corrupt, the entire downstream matching process failed. This is actually a classic hardware bug and a very rookie mistake by me. A one-cycle pipeline misalignment. Because in hardware, if you don't explicitly manage time, everything happens at once and it crashes into itself. The fix? I literally just had to tell the memory to wait one clock cycle. So everything I had to do was inserting a register in between so the data had one full clock cycle to stabilize before the command triggered, which was a very simple fix, but it took forever to find where to put it. So I thought I had fixed everything. So I hit generate bitstream one last time.
We should see all ones, right? Yes! Yes! Oh my god, this is huge. This is huge!
And finally, on the same day I was supposed to present the project, at 1:52 a.m.
Test mode, we should get score. 99! Yes! Yes! Oh, we got it. Oh, we got it. Finally. Finally.
It was somewhat working.
I mean, this is still, I'm still trying with the same image, and it's still weird. Like, it should resemble the image, like it should resemble like a skeleton of this, but you know, it doesn't.
The scores were still a little variable. There were probably some small logic hiccups in a few interfaces, but not all over the place anymore.
Also, we have squiggles, red squiggles, and they are uncanny.
The monitor was displaying something, and the same finger landed with a high similarity score. Different fingers landed low, so it was actually working. The pipeline was alive, image in and score out. And thankfully, even though it wasn't perfect, I passed the exam. This video is being recorded just as I found that out a few days later, and I am so relieved. So if you've ever wondered how a fingerprint becomes access granted, it's not a single algorithm, it's a long chain of tiny decisions. And I got that running with a cheap sensor or an FPGA. So it turns out that fast authentication is in fact very complicated and fascinating. I hope you enjoyed this. Thank you for watching.